MOSFETs are one type of FETs, other type being JFETs. J stands for junction. FET is a short form for field effect transistor. MOS stands for metal oxide semiconductor. So MOSFET, when expanded, becomes metal oxide semiconductor field effect transistor. Out of the two types of FETs, it is the MOSFET that is used widely in the present times. JFET or junction FET has almost disappeared from the scene. The structure of MOSFETs consists of a capacitor. It is called MOS capacitor. In this MOS capacitor, there exists a metal layer or metal plate. M in the MOS indicates this metal layer. Below the metal layer, there exists an oxide slab, silicon dioxide dielectric slab. O in MOS represents this dielectric. Below to the oxide layer exists a semiconductor slab. S in MOS denotes this particular plate. So MOS actually denote the structure of a MOSFET directly. Usually there exist three terminals: source, drain, and gate. Source is similar to emitter in BJT. Drain is similar to collector, whereas gate is similar to base in BJTs as far as their functionality is concerned. In FETs, the current that flows between source and drain is controlled by voltage over the gate terminal. So it is a voltage controlled device. In MOSFETs, there is also a feature. Here, source and drain can be interchanged, but in BJTs, that facility is not there. Emitter and collector cannot be interchanged. MOSFETs can be used in the design of amplifiers. They can also be used in fabricating electronic switches that goes into the making of logic gates. At present, they are used in making, in fabricating logic gates, digital circuits. They are preferred to their competitors, bipolar junction transistors, because of their size, smaller size. Field effect transistors, MOSFETs, Part 1, Series on Semiconductor Devices and Circuits, lecture number 4.12. MOSFETs are a kind of transistors used in the design of various types of electronic circuits. In the present era, in the design of logic gates, in the design of sequential logic circuits, MOSFETs are being widely used. Currently, MOSFETs are backbone of digital circuit Fabrication. In the present session, the focus is on MOSFETs structure, MOSFETs symbols, and also on MOSFETs characteristics, static characteristics. Let us start the session with a few remarks on the historical origins of MOSFETs. The MOSFET, which had a profound effect on electronic technology development, was invented by Devon Kahung and Martin Atala. Kahung was a Korean American electrical engineer known for his work in solid state electronics. While working as a researcher at Bell Laboratories, he invented MOSFET in 59, which is the basic element in most of today's electronic equipment, along with Atala. He also conducted research on high-frequency Schottky diodes. Schottky diodes are metal semiconductor diodes. He conducted research on ferroelectric semiconductors, etc. And after retiring from Bell Laboratories, he became the founding president of NEC Research Institute in New Jersey. After historical background, now we move to basics of MOSFETs. MOSFETs are also known as insulated gate FETs. FET stands for field effect transistor. MOS, MOS stands for metal oxide semiconductor. It has much greater commercial importance than JFET. JFETs are junction field effect transistors. Chip area of a MOSFET is 3 square mils or less, which is only about 5% of that of BJT, bipolar junction transistor. Here is the reason for using MOSFETs in the fabrication of digital circuits more than BJTs. Size of MOSFET is 5% or even less than the size of BJT. Miniaturization is an important benefit given by MOSFET in the fabrication of digital circuits. A few points regarding types: N-channel MOSFET, P-channel MOSFET. Two types. N-channel MOSFET is usually called NMOS, whereas P-channel MOSFET is called PMOS. Each one has two modes of operation: depletion mode and enhancement mode. Enhancement mode MOSFETs are called NMOSs. PMOS. Whereas depletion mode MOSFETs are called DMOS. So NMOS means N-channel MOSFET, PMOS means P-channel MOSFET. Each one has two modes of operation, two types of structures and two types of operations. One is depletion mode, another is enhancement mode. Depletion mode is transistor is called DMOS, enhancement mode transistor is called EMOS. The FET operation depends upon flow of majority carriers only, hence it is unipolar device. Notice BJTs are bipolar devices. In those devices, both electrons and holes play an equally important role. That's why they are bipolar devices. But MOSFETs, FETs, they are unipolar devices. Only majority carriers play important role. It is easy to fabricate and occupies less space in integrated form, IC form. Its input resistance is high, typically many mega ohms. It is less noisy than bipolar transistors. It exhibits no offset voltage at zero drain current and hence makes an excellent signal chopper. So there are several positive aspects pertaining to MOSFETs. compared to BJTs. High input resistance, less space, no offset voltage, less noise. These are all plus points. MOSFETs also have a channel. Structurally, it has a channel, and it is associated with three terminals. So sometimes a fourth terminal also exists, but usually three terminal device. Its three terminals are named as source, drain, and gate. They are indicated by S, D, G. S stands for source, D stands for drain, G stands for gate. Here it is worthwhile to remember the terminals of BJT: emitter, collector, base. We are going to see behavior of a source terminal is very much similar to emitter terminal of BJT. Drain behavior is similar to collector's behavior. Gate behavior or purpose is similar to that of base. Sometimes a fourth terminal is also present. It is usually indicated by gate 2 or body or substrate. The terminal through which majority carriers enter is called source. Here is given a definition for source. What is source terminal? Terminal through which majority carriers enter. Terminal through which they leave is drain. The source and drain regions are always the same type, either P or N type. Here is given a small descriptive definition of a channel. The region in between source and drain through which current flows is called channel. The conductivity of the channel region is controlled by voltage on the gate terminal. Here one point is required to be recollected. FETs are voltage controlled devices. The current from source to drain, it is controlled by voltage on the gate. It is voltage control. In BJTs, the control is through current into base. The current from emitter to collector is controlled by varying the current entering into base. So their control is by current. BJTs are current controlled devices, whereas MOSFETs are voltage controlled devices. When the device has P-type source drain regions, it is called P-channel MOSFET or PMOS. And if the device has N-type source drain regions, it is called N-channel MOSFET or NMOS. In DMOS transistors, there exists a diffused channel in their structure, and in EMOS transistors, it is absent. How to recognize a transistor is DMOS or EMOS? If diffused channel is present, then it is DMOS transistor. If it is absent, then it is EMOS transistor. DMOS transistors have two modes of operation, enhancement and depletion, whereas EMOS transistors have only one, that is enhancement mode of operation. This slide contains a lot of significant information pertaining to MOSFETs. Next is given some information regarding circuit symbols. Three symbols are given in A, B, and C. In each symbol, one can notice there is a capacitor. This is capacitor. Two plates separated by some distance. Here is a capacitor. Here is a capacitor. This capacitor signifies or denotes the capacitor that exists in the structure of MOSFET. MOSFET is a capacitor with two plates. One plate made with metal, another plate made with semiconductor. Two plates separated by an oxide layer. dielectric material. Presence of capacitor in the structure of MOSFET is taken into account while designing the symbols for MOSFETs. First two are DMOS type and the last one is EMOS type. A and B, these are DMOS, whereas the last one is EMOS. These three are P MOSFETs, P channel MOSFETs. When arrow directions are reversed, the same symbols become symbols for NMOS transistors. In each of these symbols, you can find gate, drain, and source. In in only B, you can find two gates, G1 and G2. In A and B, you can see arrow into the transistor. The arrow is on source. In case of NMOS transistor, will have arrow direction out of the body of the transistor. A few points regarding symbols. The gate is shown separated from the rest of the transistor, indicating that the gate metallization is electrically isolated from the channel by oxide layer, silicon dioxide layer. The E-MOSFETs are shown with a broken vertical line joining the source and drain, indicating non-conducting or zero current device with zero gate source voltage. Hence, they are called normally off. Broken vertical line indicates normally off condition. The D MOSFETs are indicated by unbroken line between source and drain as JFETs, as in JFETs, indicating the existence of a conducting channel with zero gate to source voltage. Hence, they are called normally on. Unbroken line implies normally on. Direction of arrow does not depend upon enhancement or depletion type, but it depends upon P or N-type transistor. For NMOS transistors, the direction of arrow is opposite to that of PMOS. This fact has already been mentioned in the previous slide while showing symbols. A few points regarding PMOS NMOS comparison. The PMOS devices are much easier to produce than NMOS devices. Positive mobile ion contaminants can turn the NMOS device prematurely, whereas PMOS devices do not get affected by this type of contaminants. So PMOS positive points are described here. The PMOS devices require less extensive process control for fabrication, making them cheaper compared to NMOS devices. The NMOS circuits can be smaller for the same complexity than PMOS circuits. This point is in favor of NMOS. The higher packing density of NMOS makes it faster in switching applications due to smaller junction areas. This is also a point in favor of NMOS. But NMOS channel devices require extensive process control for fabrication, making them expensive and costly compared to PMOS devices. This point is against NMOS. Here is shown MOSFET structure. Structural features of enhancement PMOS. It is PMOS because source is P-type, drain is P-type. That is why it is PMOS. This is channel. It is in between source and drain. You can find no diffused channel. Channel is there, but it is not diffused channel. That's why, for that reason, one can say it is enhancement PMOS. Presence of diffused channel or absence of diffused channel decides whether it is depletion mass or enhancement mass. Here is the substrate N-type, source, gate, drain, aluminum, terminals are there. This is metal. This is silicon dioxide layer. When a gate is with negative potential, then electrons here, negative charges, they get accumulated and they attract positive charges in the silicon dioxide dielectric material. Positive charges moving one side makes the negative charges accumulating on the other side. Here negative. This negative charge induces positive charge in the channel. Holes are induced. So negative charge, negative voltage on the gate induces holes in the channel region. It increases the conductivity of the channel region. Current from source to drain naturally increases when channel conductivity increases. So by varying the voltage on gate, it is possible to vary the current between source and drain. This is briefly about the functioning of the MOSFET. An important parameter pertaining to MOSFETs is threshold voltage. It is usually indicated by VT. A few points regarding this voltage. It is a gate source voltage VGS at which ID reaches some specified small value. Usually this current is 10 microamperes. So VT is VGST equal to VGS at drain current is 10 microamperes. Advantages of lower VT are use of small power supply voltages, compatible operation with bipolar devices, smaller switching time due to smaller voltage swing during switching, higher packaging density. There are techniques to lower VT. Those techniques are mentioned here. Use of silicon crystal with orientation of 100 using a silicon nitride layer and a silicon dioxide layer. Using polycrystalline silicon doped with boron as the gate electrode instead of aluminum. These are some techniques by which one can lower VT so that we can utilize the benefits by lowering VT value, threshold voltage value. Here is shown structural features of depletion NMOS, channel depletion with negative gate voltage. Depletion NMOS. It is NMOS because drain is N-type, source is also N-type. That's why it is NMOS. It is depletion because you can find a channel here which is diffused. Diffused channel is present. That's why it is depletion MOS. Depletion NMOS. Structural features are shown here. Source silicon dioxide, gate, aluminum, drain. Notice this is aluminum metal. This is a semiconductor. Aluminum is conductor. Channel is also conductor, conducting, separated by dielectric layer. One can see similarity between this structure and a parallel plate capacitor. Of course, one difference is there. In parallel plate capacitor, both the plates are made with conductors. Here, only one plate is with conductor, another plate is with semiconductor. Except that lot of sameness is there between them. That's why this is a capacitor. MOSFET is a capacitor. It is MOS capacitor. In fact, MOSFET is derived from MOS capacitor. That is as far as A is concerned. In B is shown a channel depletion with negative gate voltage. When we apply negative voltage. Holes get induced in the channel region. So conductivity of the channel decreases because channel is as it is n-type, it is exhibiting certain amount of conductivity. In fact, conductivity is very high. Now holes are being induced, reducing electron concentration. When electron concentration falls, naturally conductivity also falls. Current between source and drain also falls. This is one aspect one has to understand while watching the structure in B. Another aspect is a depletion layer is being formed in the channel region. That can be understood easily without any difficulty by recollecting junction diode characteristics. But the important aspect one has to keep attention focused on is this depletion region is not uniform. The width is small at the source side, it is large at the drain size. This phenomena is called pinch off. It can be understood by recollecting the fact that width of a depletion region is proportional to reverse bias voltage across the junction. Here reverse bias voltage is less when compared to reverse bias voltage across the junction on drain side. Here it is more, here it is less. As the reverse bias voltage is more, depletion region width becomes more. At a certain point, it occupies the entire channel region. This phenomena, as already mentioned, is called pinch off. A few points regarding pinch off. The pinch off voltage, VGS of also called gate source cutoff voltage, is gate voltage at which ID is reduced to some specified negligible value at a recommended VDS. It can be defined as the gate reverse bias voltage that removes all the free charge from the channel. So here in these 2 points, certain defining aspects of pinch off voltage are presented. This process starts at drain end and moves to other with increased drain voltage. It is a function of doping concentration and the channel height. As the doping can be increased to a limit set by gate breakdown voltage, the pinch off voltage may be made large enough so that drift saturation effects just become dominant. Some points regarding pinch off, important points. Now here are shown MOSFET current voltage characteristics, static characteristics, drain characteristics, transfer curve for an enhancement PMOS. In A is shown drain characteristics. Here is drain current, here is drain to source voltage. One can find several curves for different values of gate voltages. Top curve is for a gate voltage of minus 20 volts. Next one is for minus 16. Next one is for minus 12. Then minus 8, minus 4, etc. In all these curves, one can notice the existence of 2 parts. Here is one part. In this part, current is increasing almost linearly with voltage. ID is linearly increasing with VDS. This part is called linear current region, linear resistance region, triode region. These are all different names for this region. Another region is also there where current is almost constant. Of course, small increase is there, but it's very less. This part is called constant current region. We are going to see if we want amplification from a MOSFET, it has to be operated in constant current region. In this region, one has to operate it. Then only it is able to give amplification. In B is shown a transfer curve, drain current versus VGS, gate voltage. When gate to source voltage is small, here drain current is also small. After some point, drain current is increasing with the gate voltage. When gate voltage is positive, ID also very less. ID value when VGS is small, positive, that ID is usually indicated by IDSS. In this diagram is also shown threshold voltage, definition of threshold voltage. Here is shown drain characteristics and transfer curve for depletion NMOS. Earlier slide gives enhancement MOS characteristics. Here depletion MOS characteristics are given. In A is shown drain characteristics, in B is shown transfer curve. Drain characteristics are ID versus VDS for different gate voltages. Notice here also we can find two regions, linear current region or triode region and constant current region, as we noticed in case of enhancement MOSFETs. A new thing here is the curves are divided into two sets. One set is termed as enhancement, another set is labeled as depletion. In enhancement set, VGS is positive. In depletion set, VGS is negative. These two are separated by, of course, VGS equal to 0. Enhancement set is associated with large drain current, whereas depletion is associated with small drain current. From this, one can understand depletion MOSFETs. They can be operated in two modes, enhancement mode and depletion mode. Enhancement mode gives large drain currents, depletion mode gives small drain currents for the same drain voltages. This facility is not there in enhancement MOSFETs. There only one mode, enhancement mode. In B is shown transfer characteristic. It is ID versus VGS. When VG is negative, drain current is very small. When VG is positive, drain current is large and it is increasing. Positive VGS means enhancement mode of operation. Negative VGS means depletion mode of operation. Notice the presence of two modes, enhancement and depletion. Also notice more current in first mode than in second mode. With this, we come to an end to the first part of a presentation on MOSFETs. In this session, basic features of MOSFETs, their structure, symbols, properties, all are considered. In the second part on MOSFETs, we discuss some more important aspects of MOSFETs like configurations. Hope this session is useful to you. We meet again soon in another session where second part on MOSFETs is given.